In today's lecture, we are going to define integration of functions, Lebesgue integration, We know Riemann integration, but today we are going to define what is Lebesgue integration, okay? So for that, we are going to start from the elementary result that what is integration. Integration of a function is nothing but it is the area bounded by the ordinate and the x-axis, okay? So the area bounded by the two vertical line and the area bounded by the curve and then the x-axis, that bounded region, that is the area of the that area is exactly equal to integration, okay? That is what we know. And then from that, the idea we are going to generalize. From that idea, we are going to generalize and find out the Lebesgue integration, okay? So let us see integration of function, okay? So what we do is that, this is the graph of the function, and then we are going to find out the ordinate fa at point A, f of v at the point B, and then, then the area bounded by this line segment A to B, ordinate this one, and then this, the area bounded this region, okay? So this is the shaded region. This is the integration of the function f of x from A to B, okay? So integration of the function f of x from A to B is represented by this area. That is quite, familiar to us. From this, we are going to, generalize the concept and find out Lebesgue integration of a function. Good. So Lebesgue integration is more generalized than the Riemann, than the original, the classical integration, okay? So let us see. For that, let us first define a simple function. A non-negative finite valued function phi x taking only finite number of different values is called a simple function, okay? That is the definition of simple function. So a1, a2 up to an are the distinct values taken by the phi. Then you can write capital AI is equal to x such that phi x is equal to AI. X such that phi x is exactly equal to small ai. That set is denoted by capital AI. And then the function phi x can be written in this form. Phi x is exactly equal to summation I running from 1 to n ai chi ai x, where chi ai x is a characteristic function. Phi x is measurable if and only if ai are measurable. So we already know that characteristic function is measurable if the set is measurable. If the set ai's are measurable, then this phi x is also measurable. Alright. So now let us see that a simple example for a simple function whose values are a1, a2, a3 taken on the set a capital A1, capital A2, capital A3. So the simple function phi takes value small a1 at the set capital A1. The simple function takes values small a2 at the set a2, capital A2, and lastly the simple function phi takes small value a3 at the set capital A3. So that is a simple example. Now then, what is the area of this rectangle? Area of rectangle is the length of this side, and the length of this side is what? The measure of a1. Measure of a1 is the length of the interval, this one, into height. Height of this rectangle is a1, okay? So that is a1, ma1 will be the area of this rectangle. Similarly, area of this rectangle will be represented by a2, ma2. Lastly, area of this rectangle will be a3, ma3. The total area will give you the integration of the simple function phi x, okay? So integration of the simple function phi x, in this example we are taking I running from 1 to 3, small ai chi ai x is given by integration phi x dx, that is sum of the area. Whole this one will be the integration of the simple function, okay? That is coming from the classical definition of integration, and that is translate into, let us translate into it into the form of a simple function, and that is exactly what we have seen here. The integration of the simple function is equal to this one, okay? So we can generalize then. So definition, then how we define the Lebesgue integration of simple function. Let phi x is equal to summation I running from 1 to n ai chi ai x. This is simple function. Be simple measurable function. Measurable means is ai, capital AI is measurable, then phi x will be measurable. Where capital AI is equal to x such that phi x is equal to small ai. Then the Lebesgue integration or the integral of phi x is given by this formula. So it is denoted by integration phi x dx. This is Lebesgue integration, and that is exactly equal to summation I running from 1 to n ai mai, that we have already illustrated using with graphs. Now another definition, this is definition 1. Another definition: for any non-negative measurable function f, the integral of the function f is denoted by f dx, and is given by because for simple function I have already shown you how to find out the integration. For simple function we know the integration, and then for any function f, how we define integration is exactly equal to supremum integration phi dx, where the supremum is taken over all measurable simple function phi, where phi is less than equal to f. Okay, so you think about all simple function that is less than equal to f. You have a collection of all simple function that is less than equal to f. You can then for simple function, we have already shown how to find out the integration, Lebesgue integration. So you have collection of Lebesgue integration, that is collection of real number. From that you have to take the supremum. That supremum value will give you the integration of the function f. Okay, that is what the definition 2 says. All right. So let us illustrate that one graphically. F is the function and it is bounded by this ordinate. So this is a simple function, simple function. It takes value in this set a1, this much in a2, and this much in a3, like this. So simple function psi, that is less than or equal to f. So it is less than because it is below the curve of the function. Okay. So this whole area will give you the integration of the simple function psi. Alright, integration of simple function, that is some gap are there. This gap, if add up, you will get the integration of f. So therefore integration of f will be greater than or equal to integration of this simple function, where psi is less than or equal to f. Alright, so another simple function you can think about like this. So in this situation, this phi will be still less than because it is below the curve, but this phi will be greater than psi, the earlier one. Phi will be greater than psi. Okay, so that is quite clear. Phi is less than f, but phi is greater than psi. So therefore integration of phi will be less than or equal to f, integration of f, and that this one will be greater than this one. So then you think about all such possible simple function that is less than or equal to f, and then you take the supremum of the all integration of the simple function. That will give you the Lebesgue integration of the function f. Okay. So integration f dx is equal to supremum phi dx, where the supremum is taken over all measurable simple function phi, where phi is less than or equal to f. Okay. So that is the the method or definition to how to find out the integration of a given function. So for any measurable set E and any non-negative measurable function f, for any non-negative function f, and that is also measurable, and for any measurable set E, so we want to find out the integration of the function f over the set E. So how you define that one? Integration of the function f over the set E is exactly equal to integration of the product of the function f and chi E, the characteristic function. So is the integral of f over E. If E is equal to closed interval AB, then integration of E f dx is exactly equal to a to b f dx, and that is exactly equal to minus b to a f dx. Okay. So example, phi. If phi is a measurable simple function, definition 1 and definition 2 both gives a value of its integral. So now we have seen that there are two definitions of integration, definition 1 and definition 2. If phi is a simple measurable function, then definition 1 will give you one integral, definition 2 will give you another integral also. those are equal. That is what this example says, so that these values are same. All right. By solution, by definition 1, how we define a definition, integration by definition 1, for simple function, integration phi dx is equal to sum I running from 1 to n ai measure ai. Okay. By definition 2, how you define integration of phi dx, that is equal to supremum of psi dx, and that is, let us put it star, integration star phi dx, say, where the supremum is taken over all, measurable simple function psi is less than equal to phi. Okay. Since phi is a simple measurable function such that phi is less than equal to phi, so this statement is true, phi is less than equal to phi. Therefore, we have integration phi dx is less than equal to integration star phi dx. Let it be inequality number 1. Let us prove the reverse inequality. Okay. Again, if psi is less than equal to phi is a measurable simple function with distinct value bj, j running from 1 to m, and then psi is equal to summation j running from 1 to m bj chi bj, then integration of psi dx is equal to summation j running from 1 to m bj let it be equality number 2. We know that phi is equal to summation I running from 1 to n ai chi ai, but union, the function is defined on R. Okay. Therefore, the union of ai should be exactly equal to R. Similarly, union of bj should be equal to R. Okay. ai intersection aj, they are empty. If ai is not equal to j, ai intersection aj is empty. Similarly, bi intersection bj is also empty if I not equal to j. So bj is exactly equal to R intersection bj, but R you can write I running from 1 to n union ai intersection bj, that you can write in this form, union I running from 1 to n ai intersection bj, a disjoint union of measurable set. So measure of bj is equal to measure of this set, that is sum I running from 1 to n measure ai intersection bj. So using in 2, we have what we have, integration psi dx is equal to summation j running from 1 to m bj, that is summation I running from 1 to n m ai intersection bj, and that exactly equal to summation j running from 1 to m summation I running from 1 to n bj m ai intersection bj. But psi is less than equal to phi, therefore bj will be less than equal to ai if measure ai intersection bj is positive. Okay. So it follows that psi dx is equal to summation j, this one, and that is less than equal to, if you replace bj by ai, since ai is greater than bj, so from this one this will be greater. Okay. But this one is exactly equal to summation I running from 1 to n ai summation j running from 1 to m ai intersection bj, but this summation is equal to what, mai. You can write this summation is equal to measure ai. So summation I running from 1 to n ai measure ai is equal to phi dx. Okay. So it shows that integration psi dx is less than equal to integration phi dx for any simple measurable function psi less than equal to phi. It follows that for any simple measurable function less than equal to psi, this side is less than this one. Even if you take supremum also, that will be less than. The supremum is denoted by this star, integration star. So this is inequality number 4. From 1 and 4 we have the result. Okay. Statement of the theorem. Let us see, if phi is a measurable simple function, then integration phi dx is equal to summation I running from 1 to n measure m ai intersection e for any measurable set e. Alright. So integration a union b phi dx is equal to integration over a plus integration over b for any disjoint measurable sets a and b. And integration a times phi dx is equal to a times integration phi dx if a is positive number. So these are simple results we are going to prove. Number 1, from the definition we have integration e phi dx is exactly equal to phi chi e dx. Alright. So here the integration is from r to r, from minus infinity to infinity, that is over r, that exactly equal to this one. And that is equal to summation I running from 1 to n ai measure ai intersection e. So this is obvious. So number 2, using 1 we have integration a phi dx plus integration b phi dx is equal to summation I running from 1 to n ai measure ai intersection a plus summation I running from 1 to n ai measure ai intersection b. Okay, we know that a union b is equal to r intersection a union b, that is exactly equal to union I running from 1 to n ai intersection a union b, that is equal to after breakup you have this one, and this is a disjoint union. All right, so measure of this one is exactly equal to measure of the union this one union this one. Okay, so that is exactly equal to measure of this one plus this one, because this one union this one is a disjoint union. All right, so this is again equal to I running from 1 to n measure ai intersection ai, because here this is also disjoint union, so you can write in this form. All right, so ultimately what it follows that measure union I running from 1 to n ai intersection a union b is exactly equal to this one, this summation. Okay, implies that summation I running from n m ai intersection a union b is exactly equal to this one. So implies that I running from 1 to n ai m ai intersection a union b is equal to this one, this summation plus this summation. So hence this summation is exactly equal to what is this? This is multiplication both sides by small ai. This is your integration phi over the set a union b, and the left hand side is over the set a plus over the set b. Okay, so we are able to prove that one. Next, you multiply a simple function by a constant number that is measurable. That is what we are going to prove. A phi can be regarded as a simple function, because when phi takes ai on ai, a phi takes ai on ai. All right, so ai can be regarded as a simple measurable function. So a phi dx is equal to summation I running from 1 to n ai measure ai, that is exactly equal to a times summation I running from 1 to n ai measure ai. Okay, because this is for a phi, this is for a phi, this is for another one. Okay, so that is, you can take from this summation, yeah, you can take so I am missing here a, small a is missing here, but I am taking out here. All right, so that is simple, you can understand, that is a times integration phi dx. Okay, so that if f is a non-negative measurable function, then f is equal to 0 almost everywhere, if and only if integration of f dx is equal to 0. So this is also one of the important result. Let us see. If f is equal to 0 almost everywhere, then for simple function phi less than equal to f, we have phi is equal to 0 almost everywhere. If phi x is equal to summation I running from 1 to n ai chi ai x, then measure ai will be 0 whenever ai not equal to 0. All right, if this small ai not equal to 0, measure of ai must be 0. It follows that integration phi dx is exactly equal to summation I running from 1 to n ai m ai is equal to 0 for simple function phi less than equal to f. So hence integration f dx is equal to supremum integration phi dx is equal to 0, where the supremum is taken over all simple function phi less than equal to f. Okay, conversely, suppose integration f dx is equal to 0, then you can put en is equal to x such that f of x is greater than or equal to 1 upon n. And clearly integration f dx is greater than or equal to integration 1 upon n chi en dx, but this integration is exactly equal to 1 upon m en, but it implies that men is equal to 0. So but x such that f of x still greater than 0 is equal to this countable union, and it follows that m this is less than equal to this one. Okay, but the sum is 0 because each set has measure 0. So therefore you have f is exactly equal to f is 0 almost everywhere. Theorem: let f and g be non-negative measurable functions. If f is less than equal to g, then integration f dx is less than equal to integration g dx. So number 2, if A is measurable set and f is less than equal to z on A, then integration of f over A is less than equal to integration of z over A. So these are all simple result. If A is greater than or equal to 0, then integration A times f dx is equal to A times integration f dx. If A and B are measurable set and A is a superset of B, then integration of A f dx will be greater than or equal to integration of f over the B. So from the definition we have integration f dx is equal to supremum integration phi dx, where the supremum is taken over all measurable simple function phi, such that phi is less than or equal to f. Phi less than or equal to f implies that phi is less than or equal to z. It follows that supremum phi less than or equal to f, integration phi dx will be less than or equal to supremum phi less than or equal to z integration phi dx. So therefore this is true. Number 2, it is given that f is less than or equal to z on A, therefore f times chi A will be less than or equal to z times chi A on R. Alright, so using number 1 we have this one. Okay, so but what is this? This is integration of f over A, and this one is integration of z over A. So number 3, if A is equal to 0, then it is done. 0 times f is 0 and 0 times f integration, they are all equal. Alright, so if A is greater than A 0, if psi is a simple measurable function such that psi less than or equal to f, then what we have? Then phi is exactly equal to A times psi, that is less than or equal to AF. Phi is also a simple measurable function. Right, so now integration phi dx is equal to integration A psi dx. So supremum integration phi dx is equal to A times supremum integration psi dx, because A is in positive. You can take out A outside the supremum. Hence integration AF dx is equal to A times integration f dx. Okay. So number 4, since A is a superset of B, we have chi A will be greater than or equal to chi B. It follows that f chi A will be greater than or equal to f chi B. Therefore integration of this one will be greater than integration of this one. That is coming from number 1. So therefore integration f dx will be greater than integration b f dx.